Welcome to an introduction to calculus. So far you've already met different parts of maths such as algebra and geometry and trigonometry, and here's a new one in higher, known as calculus. To be able to do calculus well, you have to be fluent with indices, something we learnt in Nat 5 and really did in order that we could do higher maths. Say you had an example that said something like 4a to the power of a half multiplied by 3a to the power of a quarter. Now, one or two might already be looking at that and panicking and thinking, I don't remember how to do this. With practice, everyone, and I mean everyone, can get better at this and can end up being fluent at this, meaning that you can do one of these questions without even having to think how. But as a bit of a reminder, as we so often do in maths, think of an analogy of when it's perhaps a little bit complicated. How would I do it with simple numbers? If I was dealing, for example, with not powers of a half and a quarter, but let's say I was dealing with a to the power of 3 times a to the power of 2. Well, I know what a cubed is. A cubed is, of course, just a times itself again. A squared is, of course, a times a. And if I'm multiplying all these together, 1, 2, 3, 4, 5 terms of a multiplying one another, a to the 5. Oh, but then if I inspect this, look, there's my question, there was my answer. How did I get from here to here? I added the powers. That's the shortcut. Oh, in that case, I'll use the same technique on these more awkward numbers. So 4a to the half times 3a to the power of a quarter. 4 times 3, simple enough. I'm not going to add those numbers, right? I'm just going to do what I've been doing since primary. 4 times 3 is 12. A to the half times a to the quarter. Let's use my rule from down here. Add the powers together. A half plus a quarter. Oh, 3/4. Now, if there were more awkward fractions, I could do a fractions calculation, but hopefully you know a half plus a quarter is 3/4. And it's done. In the same way, what if I had something that said c cubed over c squared? Well, that's easy enough. C times c over c squared. Cancel terms. Cancels there, goes once. C over 1. Oh, that's just c. C to the power of 1 is, of course, c. Well, in the same way, I can now deal with a more complicated one. Now that I've got a simple example to remind me of the rule, if I had something like 8c to the power of 4, divide by 2c to the minus 3. Well, another way of saying divide is just to say that's 8c to the 4 over 2c to the minus 3. 8 divided by 2 goes once, goes 4. Oh, it's easy, that's 4. C to the power of 4 over c to the power of 3. In the same way as my example here, I subtracted my powers to get my c to the power of 1. I will subtract my powers here. 4 take away negative 3, which of course is not 1. 4 take away negative 3 becomes 4 plus 3, 4c. 4 plus 3, 7. And that's done. We're already halfway there, or nears. What about when you have something like e to the power of negative 5? And we said, what's that? Hoping by now you're beginning to remember. Oh, to get rid of the negative power, as the question said, expressed with positive indices, to get rid of the negative sign, we say swap it from the top half of the fraction to the bottom. And we did a little example of why that worked in Nat 5. Swapping from top to bottom of the fraction changes the sign of the power. So that means, if I was doing something the other way around and a little bit more complicated, what if I had something like 2 over 7e to the 4? And I said I wanted this expressed with no letters on the bottom. Oh, bring it from bottom to top. The 2's already on top. The e to the 4 moves up alongside, becomes e to the negative 4. The 7 does not move. Do not bring the 7 up with this. The 7 has its own power. If we wanted to draw it in, we could say that's 7 to the power of 1. So any numbers, any multiplying numbers, coefficients next to a letter on the bottom, when we're moving the letter from bottom to top, leave the separate number where it was. So the 7 stays underneath. The power belongs to the number directly, so it moves with it. But anything in front, anything multiplying it, stays where it was. This actually also relates to what we were saying about subtracting powers when we're dividing. Because you could say, well, there aren't any e terms on the top. And there's a 4 here. What have we got? We've got 0 take away 4. So in other words, any number to the power of 0 is just the same as 1. So 2 times 1. Oh, so if a letter doesn't appear, we could say it's there to the power of 0. So that was another rule from last year. Anything to the power of 0. Even in brackets, 7,226,000 over pi times x squared root y, close bracket, all to the power of 0, bracket to the power of 0 equals 1. Anything to the power of 0 is 1. Moving on. Nearly done on this bit now. How do you deal with 9 to the power of a half? If I said evaluate this, fraction indices, mean roots. 9 to the power of a half is the same as square root of 9, which is of course 3. It's another example. 8 to the power of 2/3. The fraction bit is the root. So that's the cube root this time, not the square root. 3 says it's the cube root of 8. And the numerator of my fraction, the top bit, just stays as a normal power. So when I get my answer, I'm going to square it. So what number times itself gives me 8? That's 2. The cube root of 8 is 2. So I've done this bit here. I'll just put brackets around just to show what's happening there. The squared bit I've not done yet. So that's still there. It's 2 squared. Oh, but 2 squared is of course 4. So my 8 to the power of 2/3 works out to be 4. You could, if you wished, say I'm going to do 8 squared and then cube root it. That would be 64. And then you could say the cube root of 64. Most people wouldn't go with that way, but the cube root of 64 works out as 4. So you could do it the other way around. But it's 99 out of 100 times easier. Take the root first. The only thing to watch for is when we do not take the root first. What if it was a negative power? Let's say it wasn't 8 to the 2/3, but 8 to the negative 2/3. Let's get rid of the negative sign first. That's 1 over, remember, swapping from top to bottom changes the sign of the power. So that's 1 over 8 to the positive 2/3. Now let's deal with the fraction power. Still 1 over. And the fraction, cube root of 8. Then we'll do the squared bit last. 1 over, we've already said, cube root of 8. What multiplies by itself and by itself again to give 8 is 2. 2 times 2 times 2 is 8. Still to be squared. 1 over 4, 1/4. Because of the negative power here. That was the indices work we did in Nat 5. That would be section A in our assignment. What about slightly trickier ones for section B in the assignment? Consider if you had to work out y to the power of 5 times y to the power of 4 over y squared. Well, as an analogy, think back please to when you had to calculate something like 2/7 plus 3/7. Something like that. You, of course, are more used to meeting it in the form of 2/7 plus 3/7. And what you did was you said, well, I know what to do here. That's just 5/7. Right? And we did the whole thing about slices of pizza. But what we were doing in our head was we were saying keep the denominator the same and just add the two top numbers together, the two numerators. Well, if that's our analogy, let's use this technique of these separate fractions coming from being the same thing as here. Well, let's do that here. Let's split the top terms using the denominator each time, just like we said 2/7 and 3/7. So this becomes y to the power of 5 over y squared plus y to the power of 4 also over y squared. Oh, subtract the powers, we know how to do that. Y to the power of 3 and y to the power of 2. Y cubed plus y squared. That's it done. Well, we could do the same thing in a trickier example. What if we had one that looked a lot worse, that looked like this? Square root x plus the 4th root of x cubed all over 3 times square root x. Well, let's change it into indices. Let's not panic. Top line becomes x to the power of a half plus this becomes x. The cubed is normal. The root part is a fraction. So that's x to the power of 3 over 4. And the bottom line, 3x to the half. Okay, well, what I now have, x to the half over 3x to the half, x to the 3/4 over 3x to the half. Separate fractions, I'll simplify and I'll subtract powers. A half, take away a half, that's just x to the 0, which is 1. Or if you like, I'm just cancelling x to the half with x to the half. Either way around, the top line becomes 1. Either because I'm saying I'm dividing something by itself and cancelling, or because I'm saying a half, take away a half is 0, and anything to the power of 0 is 1. Either way, the top is 1. Bottom number, the 3, that's not done anything. So 1/3. Plus, and over here, 3/4, take away a half, x to the quarter. That brings the x's together. Oh, and I've still got a 3 underneath because I don't move the 3. So though it looked a lot trickier here, we know all the steps. We know how to turn roots into indices which are fractions. We know how to split when there's more than one term in the denominator, just put it over in the numerator, put it over the denominator separately. And we know how to subtract powers to divide. So all we're doing is combining the different skills that we have. And as we practice, we'll get very good at it. I'll give you one that looks even worse. But again, there's no new technique here. We're just mixing different skills we already have together. Say we're asked to simplify something like 1 plus 3x all squared and all divided by 2 root x. Now, if you didn't know what to do with this, just do the bits you can. And hopefully as you do those, you'll see the next step. 1 plus 3x squared is, of course, well, anything squared, multiply it by itself. 1 plus 3x times 1 plus 3x over 2 root x. I'm going to work out the brackets first before I try and start dividing up into separate bits of denominator and so on. Through whichever method, doing a grid or because you know it or whatever, 1 plus 3x times 1 plus 3x, I would hope you get 1 plus 6x plus 9x squared all over, 2 root x. Alright, let's split it into separate fractions. 1 over 2 root x. While I'm at it, I'm just going to do x to the half. You can do it as two separate steps in working if you want, but we know that root x is x to the half. Plus 6x over 2x to the half plus 9x squared over 2x to the half. Alright, now we'll simplify it down as much as we can. If I want no letters on the bottom of a fraction, I'll take the x to the half to the top. That becomes x to the negative a half. Or as we said before, there are no x's, x to the 0, take away a half. Still over 2, the 2 does not move. The 2 does not come to the top with the x. On the second bit, 2 into 2 goes once, 2 into 6 goes 3. I'm going to have 3. That's x. Remember, if there's no term there, that's x to the power of 1. 1 take away a half is a half. Subtracting the powers gives me x to the half. And last but not least, 9 over 2. That doesn't simplify, so I'm just going to leave that as 9 over 2. X squared over x to the half. 2 take away a half. That's 3 over 2. We don't normally write x to the power of 1 and a half. We don't like mix numbers as a power. But this is 4 halves. Take away 1 half, which is 3 halves. So that would be a better way to write it. Please do not write x to 1 and a half. So it looked very complicated here, but we know how to break brackets. Once we've broken the brackets, we know how to split up, providing it's add and take away. We can split it up into separate fractions, which we did here. We know how to deal with the letter on the bottom, bring it to the top and change the sign of the power, but only the letter. We know to subtract powers when we're dividing an x term with another x term, and to cancel numbers in the normal way. Did the same thing here, and that's my answer. More difficult ones, but these are the ones on part B of the assignment. Have fun.